So welcome to the next session on our Modern Java by Example webinar series. Up to this point, we've covered some RxJava examples, looking particularly at the RxJava support for concurrency and parallelism. We've also taken a look at a very interesting CompletableFutures example that was providing a way to traverse through a recursive directory hierarchy and be able to use this to count the number of images that were reachable from some starting point, such as a URL or a path name into the file system. What we're going to do today is we're going to continue our coverage of CompletableFutures and look at a number of examples that illustrate some interesting CompletableFuture features and some of the newer features that have been added in recent years to more recent versions of Java. So with that, let me go ahead and share my screen. What I'm first going to do here is share my screen and just point out where the examples will come from today's discussion. So if you go to my live lessons GitHub repository, which you can see if you squint at the very top part of the URL bar at the top, and you scroll down here, you'll see that there's lots of examples. We're going to poke inside the Java 8 folder, and then within the Java 8 folder, there's 3 subfolders we're going to try to get to today. We'll see if we get through all of them. There's the EX27 folder, which we're going to look at first, and that shows timeouts. We're going to look at the EX23 folder, and that's going to demonstrate why you want to minimize the use of joins with CompletableFutures. And then finally, if we have time, we're going to take a look at the EX8 example. And this one will illustrate a whole bunch of interesting techniques for doing CompletableFuture operations in parallel. So without further ado, let's get started. And we're going to begin by sharing my interactive development environment, which should hopefully be open to where we want it to be. And let's see where we get this. There we go. I think that's the right one. Whoops, that's the wrong one. Hold on. Try this again. So we'll start with the EX27 example. And this example is going to illustrate how you can apply Java 9 timeouts in conjunction with the Java CompletableFutures framework. So as you're probably aware, CompletableFutures came along in Java 8, and then they've added a few things to it over time. And one of the features they added in Java 9 was support for timeouts. So I'm going to show you how to use timeouts as a completion stage method. So let's take a look at the example here. This is going to be used to check to see what the value of a flight, of the lowest cost flight from London to New York would be. I'm not sure at the moment if you can get a flight from London to New York, but assuming you could, we'll check to see the lowest price. Actually, probably now is a good time to get a cheap fare if you can actually find an airline that'll fly you someplace these days. So we're going to have a couple of fields here. We're going to have a default exchange rate if we don't get a result back from our exchange service. We're going to have the number of times to run the test to evoke different behaviors. We're going to run it for up to 100 times. We're going to define a random number generator just because we're going to randomly generate some results here. And then we have our main program, which makes an instance of the EX27 class and runs the program. So let's go ahead and take a look at this. Here's the bulk of the actual logic that we're going to look at. So what we're doing is we're going to asynchronously find the best price for a flight between London and New York City. So that's what this method does, find best price. We'll look at the find best price method in a second. It's actually just kind of a little stub. But in practice, this, of course, would be some access to a web service that's going to go and look up in a travel database to find the prices from one place to another. So that's going to find the best price. And you'll notice a couple things. First of all, find best price is going to return the price in dollars, US dollars. And we're going to go ahead and do this asynchronously. So we're going to asynchronously find the best price. So this will not block. It will simply go ahead and schedule this action, this Lambda supplier, to run in a background thread in the common fork join pool, and then we're going to get back a completable future. We're then going to combine that completable future's result when it finishes with the result of a second asynchronous operation that we're going to invoke here. And this second asynchronous operation is shown here, where we're going to go ahead and query the current exchange rate for US dollars and British pounds. So what you see we're doing here is we're going to be asynchronously looking to find the cheapest price in US dollars, and then we're going to go ahead and find the current exchange rate, which will come back as a percentage of dollars for whatever the pounds are going to be. And then we're going to do a couple of magical things here to make sure we don't time out. You can imagine these were web services. They may not return quickly. And so what are we going to do if they take too long to run? So for the asynchronous search for the exchange rate, we're going to use a new method that was added in Java 9 called CompleteOnTimeout. And what CompleteOnTimeout does is it's going to go ahead and say, if we haven't heard back in 2 seconds from this call to supply async, we're going to go ahead and apply the default rate. And of course, we'd have to guess what that would be. I think I made it 1.0, but it's whatever it is, right? Maybe that would be computed at the start of each day or once an hour or something like that. Doesn't really matter. We're not too concerned about the details here. But if after 2 seconds we don't get a result, then we're going to get an exception that'll be thrown here. If we don't get this exception, I'm sorry, if it takes more than 2 seconds, we're not going to get an exception. We're just going to get the default rate as the return value from this. No matter what happens when we get a result, be it the actual result from querying the web service or when the timeout elapses, we're going to convert the price in dollars to the price in pounds. So as you can see here, this is going to do the conversion when we get a result. Now, what happens if we don't get any result back from finding the best price? How is that handled? Well, that's handled by this mechanism, which is the onTimeout completion stage method. And what this says is if the asynchronous process takes more than 3 seconds, then throw a timeout exception. And that timeout exception will then be handled in the next phase in the chain of completion stage methods that are being called as part of this overall asynchronous processing sequence. So the next thing we do is we connect the when complete completion stage method. This is a completion stage method that's designed to be used for exception handling. And what will happen here is when complete is always called, it can't change the results in any way, but what it can do is it can go ahead and do some other things that have side effects. So in this case, if we got an exception, then amount will be null and EX will be non-null. But if we didn't get an exception, then amount will be non-null and EX will be null. Those are mutually exclusive parameters. So if we don't get a null amount, then we're going to print out the amount in pounds. If we do get an exception, then we're going to go ahead and print out what went wrong. And then the last thing we're going to do kind of here from a pipeline point of view is we're going to swallow the exception. When complete does not swallow the exception. So it just can do some side effect when an exception occurs in the pipeline of completion stage methods, but it doesn't swallow the exception. So we're going to swallow the exception by using the exceptionally completion stage method. And we're just going to ignore it because we've already done something with it. We're just going to return null. And then the very last thing we're going to do here is we're going to go ahead and block, waiting for the asynchronous processing to complete. And of course, the reason we need to do that is because if we don't block here, this program will fall off the end of main, and we won't get any results. I might show you that just for kicks to see what happens, but it's not going to do what you expect it's going to do. Okay, so I'll run this program in a second. Just for kicks, I run it multiple times in a loop so you can see the behaviors over time. Here are the various web services to make this self-contained. I just have them mocked. So find best price will delay for some random amount of time and then return some value. obviously in real world, we'd go query a web server for this, or web service. Same thing for query for exchange rate, block for a random delay, and return some factor to multiply by. And convert simply multiplies the price by the rate, and then here's just random delay. It just basically creates a random delay between 0.5 and 3.5 seconds. Or maybe it's 4.5 seconds. I think it's actually 4.5 seconds. All right, so let's go ahead and run this program and see what it does when we run it. So remember, it's randomly delaying. So sometimes it's going to work, sometimes it's not. And let's go ahead and make the screen big. One of the things you have to do if you're going to run this program is you have to make sure you enable the Java 9 features, because this timeout handling is only something that's done in Java 9. So you can see that it's working. The delays are not enough to cause exceptions. But if we run it long enough, you'll see that the delay finally exceeds the 3-second max window, waiting for the computations to finish, in which case we get the concurrent timeout exception. And you can see that also sometimes we're going to end up with the timeout occurring on querying for the exchange rate, in which case we're going to get a different exchange rate than if we go and actually successfully call that web service to get the result. Okay, so that's just the first thing I wanted to show you. What's really important about this example, in addition to showing kind of a cool mechanism of being able to use Java completable futures with web service-like mechanisms in order to bound the amount of time you wait for things to occur asynchronously, it also allowed us to talk about timeouts. And timeouts are not quite as well understood because they were something that was added later in Java. That didn't come out in Java 8. It came out in Java 9 and beyond. There's a few other features that have been added later in Java 9. And one of my tutorials on my website talks about those capabilities. Okay, so let us stop sharing for a moment, and we will take some questions. So there's a question referring to the then combine completion stage method, which is one of those interesting completion stage methods that waits for two things to finish before it continues, unless a timeout occurs. It says if the task that finishes earlier, the corresponding thread will wait for the other task to finish. That means the thread that finishes earlier could be underutilized. No, not really. The reason why that's the case is that if the thread finishes earlier, it just goes back and it goes back to the common fork join pool and just waits for something else for it to do. So threads don't block when they're finished. So it'll just be done in whatever order you need to have it done. So I wouldn't worry about that. Could you also please explain why we need the then exceptionally if we're already handling when complete? So that's something that's easy to explain. Let's go talk about that. Let's reshare my screen. So keep in mind that this code is always only going to get called back to the first question. We don't have a thread just sitting there waiting. That just means it'll get called back whenever it's ready to go. If you want to make this even more asynchronous, to really make sure nothing's waiting, we could go ahead and make this a then combine async call, which will most likely ensure that the convert operation runs in its own thread. It's probably overkill to have convert run in its own thread, of course, because it's such a fast operation. But if it was a longer running operation, that would be a way to make it even more concurrent. So when complete doesn't actually handle the exception. It's the when complete method in completable futures is very much like the peak method in Java streams. It's simply called. It's intended to have some kind of side effect, like logging something or printing something, but it doesn't actually handle the exception. It's just something that's called along the way. In the same way that the peak method doesn't really handle anything, it's just called along the way to debug or to log something. I think there's a similar mechanism in RxJava called something like doOnNext, which is also like peak or when complete. So if you were to take out exceptionally, then the exception would not be handled, and instead it would basically blow up. Your code would exit because you didn't handle the exception. So when complete does not actually swallow the exception. It just does something as the code traverses through it. And that's why we need to put exceptionally in there instead. Okay, so that's a good question. So let us now move on to the next topic. And that is this one, I think. So when I talked the other day about completable futures, I made a point of saying that you want to minimize the number of calls to join. You really don't want to have to be doing a lot of joins with completable futures. Instead, what you want to do is do the minimal set of joins. Sometimes no joins, if you can get away with it. But sometimes you need a join. So I thought what I would do here is show you an example that demonstrates the difference between using lots of joins or many joins versus one join. And we'll see what the impact is on the overall performance. So this basically says, this example shows the difference between calling join on an intermediate completable future, which will block and degrade the performance, versus simply making one call to join, thereby enhancing greater parallelism. And of course, if you can get by with no joins, that's the best of all possible worlds. And so we'll kind of show you what the program does. So here we're going to have a counter, which is an atomic integer. Hopefully you all know what atomic integer is. An atomic integer is one of the atomics classes, and it uses under the hood a very clever compare and swap algorithm to do so-called lock-free updates of data structures. So there's no locking. It just uses compare and swap, which is super duper fast, unless you have a ton of contention, and then it can become a problem because all the threads spin. But we don't have that problem here. We're then going to define a couple of different suppliers. So, or at least, let's see, we have one supplier and one function. This supplier is going to increment the atomic counter, sleep for 1 second, and then return the incremented value. So it's just there to do something. It's not particularly profound in what it does. If anybody wants to extend this example to do something more interesting, please feel free and let me know. So you can see we increment the counter by 1, and obviously this is ultimately going to be done in multiple threads, so that's why we use an atomic integer. Then we go ahead and display the results, and then we sleep, and then we display that we're leaving the supplier. And we return the result. Down here, we have another functional interface instance, which in this case is a function, and it's going to return any even numbers that are passed to it. And if for some reason an odd number is passed to it, it's going to return a null. And it prints out what value is passed in, so you can kind of debug this. Again, not the world's most profound example, but I'm really doing this just to set it up so we can demonstrate the difference between calling join and not calling join. Okay, so now we come down here and we make a list of suppliers. And as you can see, we're going to do list of, and we provide 4 copies of the supplier. So now we have a list of suppliers of integers. And I'll have to go back and check. This is one of those situations where it might be nice if we're doing Java 10 features to use the var keyword. I was playing around with var the other day, and it was driving me crazy because var is extremely limited in what you can apply it for. So let's have some fun here. We'll see if this works or not. We'll comment out, we'll comment out this code, and let's cut that, and let's do this, and then let's say var, and we'll see if this is going to work. I hope it works, because I would like to be able to use var. var is kind of limited because there's certain kinds of expressions you can't use it with, and of course they're the ones that are most interesting as far as I can tell. So then we're going to go ahead and run 2 tests. We're going to run one test called test many joins, and then we're going to run another test called test one join. And as the name implies, many joins is going to test many joins, and test one join is going to have one join. And we use the same little timer mechanism we looked at the other day, which just times the time required to perform the operation, which in this case is basically a runnable. And when we're all done, we go ahead and print the results. So let's now go ahead and take a look at the tests. So we have test many joins. And what this is going to do, as you can see, is it's going to go ahead and create a stream of the suppliers, because we got n of these, we have 4. And then for each of these things, we're going to go ahead and run each supplier asynchronously. by basically passing in supply async here. This is kind of clever. What we're doing is we're taking each supplier, and that's what supply async expects. It expects a supplier, and we're going to basically call map on every one of these things. So if we have 4 suppliers, we're going to end up with 4 calls to supply async. Each call to supply async will go ahead and run the supplier in the background using a different thread in the common fork join pool. Then what we're going to do, and this is going to be sort of the wrong way to do this, we're going to go ahead and we're going to filter the results. And what we're going to do here is we're going to take the future that came back from each of these things, and we're going to apply it, and we're going to join. So join is going to block until that call finishes. So each of those calls is now going to block. So we're calling filter, they're going to block, and then we're going to check whether we got a null or a non-null back. And of course, we're going to ignore all the nulls, and we're going to collect the non-nulls, and we're going to collect these things into a future using that really clever futures collector we talked about the other day. And then when all those calls are finished, we're then going to go ahead and accept and display the results. So we're going to print all the results out. And we're going to join at the very, very end of this just to make sure it doesn't fall off the end. But you can see that the test many joins method will call all these intermediate joins, which is going to turn out to be a problem. Let's now go ahead and take a look at the test one join method. This is going to be a lot more efficient. So we're going to go ahead and once again create our list of suppliers into a stream of suppliers. Then you're going to go ahead and run all the suppliers in parallel using supply async. And this time, instead of using filter, we're going to use map. And map is going to go ahead and call then apply. And so this particular call, unlike the one we saw up here, doesn't call join. It just goes ahead and uses the CompletableFuture's built-in behavior, which is to essentially register this action to be called when the previous stage finishes. You'll also notice how this particular approach is clever because it combines CompletableFutures, which give you this asynchronous processing, with sequential streams, which give us this wonderful way of structuring the code in a more intuitive way. So we don't have to have loops, so we don't have to do other kinds of things with conditional expressions and so on. Once again, we take this stream of intermediate results and we collect them into futures. And then when everything's done being processed, we're going to go ahead this time and take the stream of results, filter out everything that's null, so we only have non-null results, and then collect the results into a list and print it. So we'll end up with the same output for each of these things, but one is going to run faster than the other. And then, of course, we put a blocking call to join. And here's the display method. This just kind of shows you what thread the caller, the string was passed in, what thread the calling program was, or calling piece of code was running in when it was called. All right, so armed with all of that, let's see if we can compile this and run it. And hopefully it'll work. Yep, cool. We were able to use that var. And you can see here the difference. And this is, I mean, once you understand my code setup, you'll understand exactly why we got the results we did. First, let's just look at the results. So test one join took about a quarter of the time as test many joins did. And the reason for that's very clear. We had 4 suppliers running in parallel. I've got a 6-core machine. And so as a result, all of those calls were able to run in parallel at the same time because they weren't joining on intermediate results. In contrast, test many joins were all joining on the intermediate results, and therefore they were wildly underutilizing the amount of available parallelism on the machine. And this just shows you the way this is working. So we go ahead and run test many joins, and so it's just displaying the outputs as we're going along. And if you look at this, you'll also see that the test many joins is much more regularized in terms of the order in which things run, and that's because they're over synchronizing with the use of join. In contrast, the test one join, not only does it run fast, but you can also see it runs more asynchronously. So it has a bunch of suppliers starting up, and then it'll leave the suppliers. And those are kind of interspersed and interleaved with the other processing. And that's because all of this processing is actually taking place literally in parallel. And so we're getting results that are more sensible for what we're doing. And then the final results, of course, only print out the even numbers, not the odd numbers. So hopefully that gives you a little better understanding of the consequences of using join too liberally in your code, and how you can rearrange your code to not use join. Something else I'll mention very briefly, because this is also part of the magic of this example, is we use this super cool stream of futures collector. I had shown a variant of this a couple days ago when we talked about the web crawler example, the recursive directory hierarchy crawler example that used completable futures. In that example, I had a futures collector that worked on a list. This time we're going to have a futures collector that works on a stream. So let me just cover that real quickly because it's interesting to know about. So stream of futures collector is something that's based on a posting from Thomas Nukowitz, who's a completable futures and RX Java expert. And I liked what he did, but I wanted to make it work in the context of streams. So I made a collector that did this. And stream of futures collector is a collector that's going to work on a stream of completable futures. It's going to collect them into a list of completable futures, and it'll return a single completable future to a stream of completable futures that are off processing in the background. And notice how this is a parameterized class, so it is going to be working on lists and streams of type T. The particular method implementations are all factory methods. The supplier returns an array list as a constructor reference. The accumulator, can't quite see it here, let's move it over. The accumulator is going to go ahead and return a method reference that will be used to add a new completable future into the accumulator, which is the so-called mutable result container. And those are always used for either sequential or parallel streams. Combiner is only used for parallel streams. It's used to combine together two partial results. We don't use parallel streams here, so I'm going to kind of skip that. It just sticks one thing at the end of the other. And the interesting method here, of course, is the finisher. The finisher is what's called when we're all done accumulating everything into the stream, from the stream into the mutable result container. And that, in this case, is going to return to us a completable future to a stream of objects. And the way that this works under the hood is it's going to use the arbitrary arity method all of, which is defined on CompletableFuture. And it's basically going to take the list of completable futures that we have collected, convert that into an array of completable futures, pass that array of completable futures to all of, and keep in mind that those are completable futures to computations that are running in the background, so they're off doing their thing. And then we get back a single completable future from all of, and that completable future will trigger if and only if all of the other completable futures have finished. So when that happens, we then go ahead and apply this completion stage method, which will then take the list of futures, turn them into a stream of futures, and then go ahead and map the results to join with each of the elements. The call to join here never blocks, or the calls to join never block. And the reason they never block, of course, is because we never would have gotten this piece of code called in the first place had not the single completable future returned from the all of operation completed, and it only completes when all the completable futures that it's waiting on have completed. So what gets done here is we end up returning basically a completable future to a stream of objects. And that's because there is no terminal operation here. So what we're getting back is a stream as the result. And so that stream can then be used by the main program up here in order to be able to take the stream of results and then go ahead and collect them into a list and display them. Anyway, so that's basically what's going on here. So it's very cool, very powerful, and lets us work with these things in all kinds of interesting ways. All right, so let me go ahead and see if there's any more questions. So, what's the difference between lock-free and wait-free algorithms. So this is really outside the scope of this talk. So lock-free algorithms basically say that you're not going to acquire a lock. So obviously things that are stuff like the atomic longs and atomic integers, those just spin. Wait-free algorithms are a different class of algorithm that have other properties where you don't ever have to block. You may lock, but you may not have to wait. So if you Google wait-free algorithms versus lock-free algorithms, you get lots of discussions of that. Another question: what are the problems if we use parallel streams and completable futures together? There's no particular problem. It's just kind of overkill. So parallel streams are going to try to break things up based on splitterators on the data source. And then, of course, the completable futures are going to try to run things asynchronously in the background. So you'll just probably end up with just more concurrency than you really can, or more parallelism than you can really use. I suppose if you had a 1,000-core machine, it might be worthwhile trying to do something like that. But in general, it just makes the program more complicated to debug and probably doesn't give you much bang for your buck, if you will. Why does the comment say asynchronously apply on line 140? Let's see. All right, so we'll take these in 2 steps. So I think I can answer the first question earlier. How does finisher work in the case of infinite streams? Well, obviously, you would never have an infinite stream if you were using streams framework in the way that we've shown here. So for the examples we're using here, where we're dealing with collections, you don't have an infinite collection. And so as a result, you wouldn't be using something like that in that case. So the question doesn't really make sense. If threads go back to the pool, then there could be the overhead of context switching. I'm not quite sure what you mean by that. So in general, context switching, well, a couple things. First of all, context switching these days on modern multiprocessors is pretty fast. Number 2, if you use a pool of threads, that's always the issue, right? I mean, the whole point of using a pool of threads is to be able to have different threads do the work. And the other thing is, if the work that you're doing is going to take more than a very small amount of time, the overhead of context switching is negligible. So I'm not sure quite what that really means. Let's see. We're calling that apply, which is synchronous, right? So let's take a look at the example. This is line 140. And we'll go up here. Let's see if I can find line 140. Let's see. So, this is an interesting question. So, remember that the way that the completable futures work is the actions that take place occur in the context of whatever just happened. And since whatever just happened is occurring in the context of these threads running in a pool, there will be multiple threads running. We know that there's at least 4 of them because I've got a 6-core virtually hyper-threaded machine. So we have lots of things that are running. Each of those things is running in its own thread, because each of those operations is running in its own worker thread from the fork join pool. And when each of those worker threads finish, they're going to turn around and say, oh, I need to apply this next action. Now, it's correct that the action that's invoked by then apply is synchronous, but it's running in an asynchronous context, of course, because it's running in one of the threads that was created by supply async. So as a result, it is actually asynchronous with respect to the overall flow of control here. Okay, so let's go back and see if there's any more questions. Let's see. I mean, the context switching with regard to then combine, the thread goes back to the pool. So let's see, or I guess at this point, you're now referring to the previous example. So let's go back and look at that as far as I understand, because this example here didn't actually have then combine. So let's go back over here to my screen, and let's pop out over here. And so here we can see there's a couple of different approaches. This particular approach simply says, so then just recap on then combine. Then combine is an example of a completion stage method that will only trigger when both of its previous stages complete. And as you can see here, in this particular example, we have one set of processing taking place in one worker thread in the fork join pool that's spawned by supply sync. And then we have another action that's taking place in a different thread in the common fork join pool, which is taking place as a result of this supply sync. So one thing's looking for the price, one thing's looking for the exchange rate. And in this particular example, what's going to happen is whoever finishes first, they're done, and that thread goes back and waits for the pool. I mean, what else would you want it to do, right? It shouldn't sit around and block at that point. It just goes back to the pool. And at that stage, the next thread that finishes will be the one that will trigger the actual call to convert. So whichever one finishes second is the one that's going to end up running the convert method. So that's perfectly fine. That thread has nothing better to do at that point. Let's keep it going. So there's no unnecessary context switches there at all. The point I made earlier was if we change then combine with then combine async, in that particular case, this action here, the then convert, or sorry, this convert operation is likely to run in another thread in the fork join pool. Now, it might end up running in the same thread because that thread may have nothing else to do, but it also could end up running in a different thread. And as I pointed out, for something as quick as doing the conversion, which just multiplies the price by the rate, it's probably overkill to put that into another thread. And that would be sort of the overhead of context switching. So that's why I didn't do that. And that's why I just kept it with then combine. So hopefully that answers your question about how this all works. So just to recap, the thread that finishes first for then combine obviously goes back to the pool. No harm done. That's what it needs to do to handle other work. The thread that finishes second continues to do the operation that's defined for then combine. And again, no extra context switch there. And when it's done, it'll go back to the pool. So we don't really count context switches when something goes back to the pool because it's got to go back to the pool if it wants to be able to do more work. Okay, so that's basically what I wanted to cover in today's discussion. What we have for future topics, let's go ahead and go back over here, and I will try to find my web browser. There we go. So in future discussions, we will continue to cover, obviously, completable futures. I'll see if I can find some other cool examples of RX Java to show you. I'd really like to do an update to the RX Java. I'd like to do an update to the recursive web crawler example using RX Java instead of using completable futures. I think that would be quite interesting to see and compare and contrast the performance. We do have another interesting example that I'll look at some point, showing off a whole tour de force of completable future mechanisms that we can look at later. And then there's all kinds of other stuff that we could look at too, having to do with parallel streams or the fork join pool and so on. So that'll be stuff that we can cover in future sessions. But before we stop today, let me just see if there's any other questions. Will I continue this webinar next week? Probably. I have plenty of material, as you can see if you go to my website and look at the live lessons repository. There's a lot of stuff there. So as long as people are interested in showing up, I'll keep doing this. And please don't hesitate to post questions either on the YouTube playlist where my videos are being hosted every day, or of course also if you go to the various Facebook pages to see that stuff as well. Speaking of YouTube, let's take a quick look here. Let me go ahead and share my screen again. If I can bring it back to the foreground. Let's see. All right, so where did that go? There it went. So here you can see that we've got the 3 videos that have been downloaded or uploaded so far, covering the various topics that we've talked about here. We've had a good number of people come and view them so far, which is great. Let's also, just for kicks, go over to my channel and go look at the community tab and see if there's any more votes. So it looks like we're split sort of, half and half between Completable Futures and RX Java. So I'll certainly take that into account for future. If you haven't had a chance to vote and you'd like to see some of these other topics, obviously don't hesitate to vote and don't hesitate to pitch in. People may also want to see other things. So there's a question here about synchronizers and concurrent hash map and so on. Happy to talk about any of those things. Got lots of examples. There's also lots and lots of videos on those topics that you might want to take a look at. Let's go back to my website for a second. So if you go over here and we get rid of this and we go here. If you want to learn more about synchronizers and completable futures and so on, you probably want to go here. And this is the course I've been teaching at Vanderbilt this semester. And it covers everything you could possibly ever want to know about Java synchronizers. It covers everything you might possibly want to know about things like the Java executor framework. And it also has a fair amount of coverage on the concurrent hash map stuff as well. Let me see if I can find some examples. So if you take a look here, like in week 8, for example, there's a bunch of videos about concurrent hash map and other concurrent collections and synchronized collections and so on and so forth. There's stuff in week 7 about synchronized collections. So that's a good place to go if you want sort of comprehensive coverage of all these topics. My focus in these webinars that I'm doing here is really more the by example stuff. I want to take an interesting example and kind of walk through it in detail. And if you're looking more for concept videos about how to use semaphores or how to use rantrant locks or how to use concurrent hash map, those concept videos are found in my existing material. If you have specific questions about any of those things, of course, please feel free to watch them and either post them as a comment on the YouTube video itself or come to the class next week or tomorrow, and we'll talk about those things. Okay, well, thank you guys again so much for coming, and I will look forward to talking to you soon. I'll be doing this again tomorrow, so please don't hesitate to come back, and we'll talk later.